Today we shall consider the topic finite state automata. This is a very useful topic, it has got lot of applications. It finds use in the lexical analysis part of a compiler. You know that a compiler is a very big program which translates a high level language into a machine language, and it has got several parts. And in the lexical analysis part of a compiler, the idea of a finite state automaton has found a lot of use, and it is also used in text editing and in computer networks and in image compression and so on. There are a lot of applications for that. Though we may not study all of them, I will indicate to you the application of finite state automaton in the lexical analysis part. Actually, if you know about sequential circuits, the finite state automaton is an abstract model of a synchronous sequential circuit. So, let us start with the serial adder and go into the concept of a finite state automaton. Consider two binary numbers and consider the addition of these two numbers. 1 0 gives you 1, 0 1 also gives you 1, 1 1 gives you 0 with a carry 1, and that carry along with this 1 gives you a 0, and there is carry, and carry the 0 0 gives you a 1. Now, there is no carry. This 1 1 also gives you a 0, and there is a carry, and that is given here. Now, if you want to represent it as a state diagram like this, this is called a state diagram. First you get 1 0, the input is 1 0, then the input is 0 1, then the input is 1 1, then 0 1, then 0 0 1 1. The output is 1 1 0 0 1 0 1. Let us see how you get this from this diagram. First you get a 1, you are starting in the initial state q naught, which is marked like this. Then in this you get a 1 0. A 1 0 gives you a output 1 and you go here. That is what you get. Then you get a input 0 1, then also the output is 1 and you go here. Then you get a input 1 1, so the output is 0 and you go here, and then you get a input 0 1, so you get 0 as the output and you go here. Then you get the input 0 0, so you go here with the output 1, and from here you get the input 1 1, so you output a 0 and go here, and from here you get a 0 0, that is there is no output. The last output for this there is no input, but without last you can assume it is 0 0. So, you go from here you get a 0 0, you output a 1. Now, here the input is a pair of binary digits 0 0, input is either a 0 0 or a 0 1 or a 1 0 or a 1 1, 2 digits. Output is 0 or 1. In the diagram, the input is written first with the slash and the output. So, let us write the inputs like this. This is the one which you are going to get first, then this and so on. So, first you get 1 0, then 0 1, then 1 1, then 0 1, 0 0, 1 1 and 0 0. So, initially you are starting in state q naught. After getting a 1 0, you are again in state q naught, and after and at that time the output will be q naught 1 0 gives you an output 1. Then next you are in state q naught and you get 0 1. So, you go to Q0 again and the output is a 1. These two are called states. So, from Q0, if you get a 1 1, you go to Q1 and the output is 0 now. From Q1, if you get a 0 1, you go to Q1 again and the output is 0. From Q1, if you get a 0 0, you go to Q0 and the output is a 1. From Q0, if you get a 1 1, you go to Q1 and the output is 0. From Q1, if you get a 0 0, you go to Q0 and the output is a 1. So, when the inputs are 1 0 0 1, 1 1 0 1 0 0 1 1 0 0, that is this sequence. The sequence of states will be Q0 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 Q1 Q1 Q0 Q1 Q0 and the output will be 1 1 0 0 1 0 1, 1 1 0 0 1 0 1. This is what you get and this is you get from this diagram. Now, when you look at this diagram carefully, you see that this state Q0 corresponds to a no carry state. When there is no carry, the machine is in Q0 and when there is a carry, this corresponds to a carry state. When you read two binary numbers, digit by digit, that is pairs of digits you read, then after reading a particular portion, either there will be a carry from the previous digits or there will be no carry. So, when you see that initially when you start there is no carry. So, when there is no carry, if you add a 0 and 1, you get 1. Again there is no carry. Without a carry, then when you add a 0 and 1, you get 1. And now also there is no carry, but when you add 1 and 1, you get the output 0, but there is a carry. So, you have to distinguish between two types of states. One is when there is a carry and the other is when there is no carry. The whole thing can be represented by a diagram like this. This is called a state diagram and this is an abstract model of a synchronous sequential circuit. You know that a serial adder is a synchronous sequential circuit and the abstract model is represented like this. Now, let us consider one more example. Consider this example. Q0 and Q1. When you get a 0, output is a 0. When you get a 1, the output is a 1. When you get a 0 here, the output is a 1. When you get a 1, the output is a 0. Here the input is the symbols 0 and 1, that is also the output. Q0 is the initial state. The initial state is marked by an arrow like this. So, suppose I get the input 0 1 1 0 1 0 0 1, suppose I get this input. What will be the state sequence? State sequence. Initially the machine is in Q0. When you get a 0, it goes to Q0 again and the output, what will be the output? Output will be 0 here. In Q0, if you get a 1, you go to Q0, if you get a 1, you go to Q1, state Q1. Here again the input and output are written with a slash. First symbol is input, then slash, then the output. This is the convention with which we write. So, in Q0, when you get a 1, you go to Q1, and then the output is a 1. In Q1 when you get a 1, you go to Q0 and the output is a 0. In Q0 when you get a 0, you are in Q0 and the output is a 0. In Q0 when you get a 1, you go to Q1 and the output is a 1. In Q1 when you get a 0, you remain in Q1 and the output is a 1. In Q1 again when you get a 0, you remain in Q1 and the output is a 1. In Q1 when you get a 1, you go to Q0 and output a 0. Now, if you look at this very carefully, this is the input 0 1 1 0 1 0 0 1 and this is the output 0 1 0 0 1 1 1 0. Now, this is the time with which you start, time t is equal to 0, t is equal to 0 output. Then the time after reading time 1 you read this, time instance 2 you read this, time instance 4 and so on. Now, what does this do? Say at time 5 you have read this portion of the input and what is the output at time 5? 1. At time 6 you have read this portion and what is the output? 1. At time 8 you have read this portion and what is the output? That is 0. At any time instant, the output denotes the number of ones you have read so far, whether it is an odd number of ones or even number of ones. So, this machine is actually a parity checker. This is a parity checker. So, at time instance 0, you are in Q0, then at time instance 1 you read a 0 and output by 0, that is so far you have not read any 1. So, even parity. Now, next you read a 1, so you have read 1 1 up to this point, so the odd parity, so you get 1. At the next instance you have read 2 ones, so now you have read even number of ones, so even parity you get a 0. So, fourth instance also you get a 0. So, this tells you that you have read an even number of 0. So, the output is a 0. So, whenever there is even parity, the output is 0. So, you get this even parity, you get output 0. Odd parity is denoted by the output 1. This is known as a parity checker. This is again a state diagram and there are two states Q0 and Q1 and input and output are written like this, input / output, and this is known as a finite state automaton. So, this is another example. You know that parity checker also can be implemented by synchronous sequential circuit and this is an abstract model. Now, apart from this, let us consider a simple one. Suppose you are having a TV and when you switch on the TV is initially off, then when you switch on it goes to the on stage, when you switch off it goes to the off stage. This is a small instance of a day to day life which you can represent it by means of a state diagram like this. In general, a state diagram consists of the following things. It has states written in the form of a circle. States will be written like this. They are called states, and the initial state will be denoted like this. You have initial state marked. Then transitions, they are marked by arrows, and on the transitions you have input / output. And later on we shall consider that you can look at it as also as a recognition device, in which case you will not talk about output but only input, but some of the states will be designated as final states. So, let us consider one more example, which is like this. This also has got two states, and the input can be 0, 1, which is also the output. In that case, when you get a 0, the output is a 0. When you get a 1, you go to Q1. In Q1, when you get a 1, you remain there. Again, when you get a, in Q1 you get a 0, you go here, but the output will be a 1. So, this is another state diagram of a machine, and let us see what this machine does. Let us consider the state sequences. Initially you are in Q0, and when you get a 0, you are in Q0. In Q0, when you get a 1, you go to Q1. In Q1, when you get a 1, you go to Q1. In Q1, when you get a 0, you go to Q0. And in Q0, when you get a 1, you go to Q1. And in Q1, when you get a 0, you go to Q0. And in Q0, when you get a 0, you go to Q0. And in Q0, when you get a 1, you go to Q1. Now, let us see what is the output. The output is Q0 0 is 0, Q0 1 is 0, Q1 1, output will be a 1, Q1 0, you go to Q0, but output a 1, and Q0, when you get a 1, you output a 0 and go to Q1. In Q1, when you get a 0, you output a 1 and go to Q0. In Q0, when you get a 0, you go to Q0 and output a 0. In Q0, when you get a 1, you go to Q1 and output a 0. Now, you look at it carefully. What does the output represent? The output represents like this. Leave alone the first output. The first output will be 1, 0 here always. Afterwards, look at the input sequence and the output sequence 0, 1, 0, 1, 0, 0. So, the same input you are getting here except for the first one will always be a 0. And you are in state Q1 now. Next, whether you get a 0 or a 1, you are getting a Q1. Next instance, you may get a 1 or a 0, but the output will be a 1. Next instance, whatever may be the input, the output will be only 1. So, if you forget about the first output, the same input sequence you are getting here, and this machine is called a one moment delay machine. One moment delay machine. The first output is 0. Afterwards, this input is output one instance later. Second instance you get 1, but you output what you got at the first instance. Third instance the input is 1, but you are outputting what you got at the second instance, and so on. That is why this machine is called a one moment delay machine. This is again another example of a finite state machine. So, like that we can consider several examples. So, in all these examples we have input, we have output, but we did not say anything about final states and so on. You can also look at the finite state automaton as a recognizer or an acceptor. It is accepting strings. You consider an input alphabet sigma and consider strings over sigma. This is denoted as sigma star, this we know. Strings over sigma are denoted by sigma star. A finite state machine can be designed such that it accepts a subset of sigma star. Let me consider one example. Look at this machine. The alphabet is AB. Let us consider this diagram. There are 4 states Q0, Q1, Q2, D. Now, you see that you are not marking any of them like input slash output, the transitions. It has only one symbol which denotes the input. Now, you are bothered only about the input. And you see that this state is marked with a double circle, that is called a final state, and this is the initial state. Now, if you traverse a path along for a string, for example, consider the string A, B, B, this is the input. What will be the state sequence for this? Q0, A will give you Q1, Q1A will give you Q1, Q1A will give you Q1, Q1B will give you Q2, Q2B will give you Q2. So, for the sequence A, B, B, A, B, B. So, after reading the string A, B, B, you reach the state Q2, which is a final state. So, given a string, you start with Q0, and after reading the whole string, if you reach a state which is a final state, that string is said to be accepted by this finite state automaton. Consider this string BAA or consider the string ABA. What will be the state sequence for this? This is Q0, Q0 B will be D. Why I am calling it as D and not Q3 will be clear in a moment. DA is D, DA is D. Similarly, start from here. Q0 A is Q1, Q1 B is Q2, Q2 A is D. After reading these strings, you are in the state D, which is not a final state. So, these two strings BAA, ABA, they are not accepted by the machine. Look at this string also AAA, start from Q0. After reading A, you will be in Q1. After reading A again, you will be in Q1. After reading A, you will be in Q1. Q1 is not a final state. So, this string also cannot be accepted by the finite state automaton. So, starting from the initial state, after reading the string, if you reach a final state, the string will be accepted. So, you look at this string will be accepted, whereas this string or this string or this string will not be accepted by this machine. So, if you look at the diagram very carefully, you will realize that any string where you have a sequence of A's followed by a sequence of B's will be accepted, but there should be at least one A and one B. There should be one A and one B. So, a sequence of A's followed by a sequence of B's will be accepted by this machine with the condition that there should be at least one A and one B. Any other string will not be accepted. So, this is the idea of a finite state automaton as a recognizer. Let us see the formal definition. Now, before going into that, the idea is represented like this. You have an input tape in which you have the symbols. Say for example, here you have the symbols. There is a finite control. This is called finite control, which represents the state of the machine, and there will be an input head. Initially, the input head will be pointing to the leftmost symbol of the input tape. This is the input tape. So, now the input is A, B, B, and initially the machine will be in state Q0, which is the initial state. Then at any particular instance, depending upon the state and the symbol, you go to the next state and the input pointer will be moved one point to the right. So, let us consider this example. So, initially the machine is in Q0 reading the symbol A. What is Q0 A? Q0 A is Q1. So, the next instance it will go here, input pointer will be moved and you will be in state Q1. In Q1 it is reading a. So, depending upon the state and the symbol, it will move the pointer to the next cell and the state will be changed. What is Q1A? From this diagram, you can see that Q1A is Q1. So, here you will get this. So, in state Q1 again it is reading a. Q1A is again Q1. So, it will move its pointer here and it will be reading this in Q1. Again Q1A is Q1. So, the input pointer will be moved and you will go to the next cell. What is Q1B in the diagram? Q1B will be Q2. So, from Q1B you will get the machine will go to Q2 and the input pointer will be moved next. In Q2, if you read a B, you will get only a Q2. The next state will be Q2. So, now the input pointer will be moved and you will go to this cell in state Q2. In Q2 again you are reading a B. So, the next state is Q2. So, after reading the whole input, you are in state Q2, which is a final state. So, initially you start reading the leftmost symbol in the initial state, and after reading the whole input, if you reach a final state, the string will be accepted by the automaton. If you reach a non-final state, then the string will not be accepted by the automaton. So, let us go to the formal definition. A finite state automaton, M is a phi tuple. M, it is denoted formally like this: M is equal to K sigma delta Q naught F, where K is a finite set of states, sigma is a finite set of input symbols, Q naught in K is the initial state, one of the states is designated as the initial state. A subset of the set of states is designated as final states. F contained in K is the set of final states. Delta is a mapping from K into sigma into K, or you denote delta as K into sigma into K. And the whole thing is denoted by a state diagram like this. The states are marked with circles. The initial state is marked with this. The transitions delta mappings are denoted like this. The whole thing can be represented by what is known as a state table also. State table. There will be one column corresponding to each input symbol, and there will be one row corresponding to each state: Q0, Q1, Q2, D in this particular example. Let us consider this example. The initial state is marked like this. Q0 is the initial state, so it is marked like this, and Q2 is the final state, which is marked like this. The transitions are marked in the state table like this. What is Q0 A? Q0 A is Q1, Q0 B is D. So, Q0 A is Q1, Q0 B is D. What is Q1 A? Q1 A is Q1, Q1 B is Q2. Q1 A is Q1, Q1 B is Q2. Q2 A is D, Q2 B is Q2. So, this is D, this is Q2, DA is D and DB is also D. So, the same diagram you can represent as a table like this. You see that each cell contains a single state and so on. Why the state D is, I am denoting as D, is once you reach this state, afterwards you cannot go to any final state. So, the string has to be rejected only. So, such a state is known as a dead state, dead state. D corresponds to a dead state here, that is why we are calling it as D. So, we have seen that a finite state automaton is a phi tuple and it has got 5 components: K, sigma, Q naught, F. We have seen what is that. Delta is a mapping from K into sigma into K, and this transition, this is called the transition mapping, transition, and that can be represented by a state diagram like this or by a state table like this. Now, let us define the language accepted in a formal manner. Now, extend delta to delta bar, where this is from K into sigma star to K. delta is from k into sigma. Now, you are extending it to k into sigma part into k. You define like this: delta cap q epsilon, the empty word, equal to q for all q in k, and if x is a string and a is a symbol, then you define delta cap, because q belongs to k. What can you say about delta of qx, delta cap qxa? That is equal to delta of delta cap q of x comma a. In essence, it means like this: you have a string x, the last symbol of which a, you start in the beginning with the state q. What is the state to which you go after reading this x a? That is denoted by delta cap q of x a. That is, after reading q x, you will be in a particular state, and from that state, say p, then from that state you read a symbol a and go to a state. So, after reading x, you are in a state, and from that state you read a and go to this state, say r. This is what is meant by this. Now, if you look at this carefully, for a single symbol, delta cap q a is the same as delta of q a. So, we need not have to write delta cap and delta cap. Actually, delta cap is when you have a string, and delta is when you have a single symbol. Because they are the same, when you take a single symbol, you need not have to distinguish and write two different symbols. You can just use the symbol delta itself. So, what is the language accepted? The language accepted is denoted by this. Sometimes it is denoted as LM, sometimes it is denoted as T of M, where M denotes the finite state automaton. That is the set accepted, set of strings accepted, strings accepted, and that is denoted by set of strings of the form x belongs to sigma star delta of q naught x belongs to f. So, the set of strings which take you from the initial state to a final state, or when you start reading a string starting with the initial state, and if you reach the final state, such a string will be accepted by the machine. That is what we have seen in this example also. So, the language accepted is denoted like this. Let us consider a few more examples. Let us take the alphabet. Sigma is equal to AB, input alphabet is this. Look at this diagram. There is only one state and you have this diagram. What is the set of strings accepted? Any string, if you take consisting of A's and B, after reading that starting from Q naught, you will be in Q naught only, there is only one state. So, the set accepted or the language accepted is just sigma star in this case. Any string of A's and B's will be accepted by this machine. Let us consider this example. Q naught is the initial state as well as the final state. There is a state Q1. If you read a you go here. If you read a B, you go here. Then there is one more state. This. What is the set of strings accepted? If you get a string of the form, say A B A B A B, start from here A B A B A B, you will reach a final state Q0. So, any string of the form A B A B A B A B like that will be accepted by the machine. But if you have a string of the form A something like that, or a string beginning with a B, what will happen? A, you will go to this, afterwards you will remain in state D only. Similarly, if the string begins with a B, you will go here and afterwards you will be in the dead state only. Once you reach a dead state, you cannot go back to the other state, so string cannot be accepted. So, the language accepted is the set of strings of the form A B power n greater than or equal to 0. What do I mean by n greater than or equal to 0 is epsilon, the empty string, will also be accepted by this machine. This machine accepts the empty string also. When does epsilon get accepted? If the initial state is a final state, the empty string will be accepted. If the initial state is a final state, the empty string will be accepted. Look at this diagram. What sort of strings will be accepted by this machine? Here you are having two states Q0 and Q1, and Q0 is the initial state, Q1 is the final state. Here also any string of A's and B's will be accepted. First you have a then you can have any string, first you have a B and then you can have any string. So, any string of A's and B's will be accepted, but Q0 is not the final state. So, at least one symbol should be there in the string to get it accepted. So, epsilon will not be accepted by this machine. This machine does not accept the empty string, but any other string of A's and B's will be accepted. So, the language accepted is sigma plus any string of A's and B's will be accepted, but empty string will not be accepted by this machine. So, the language accepted by this is sigma plus. Let us consider a few more examples. So, this idea is clear. Look at this machine Q0, Q1, Q2, A, B, A, B. Make the initial state as the final state. So, epsilon will also be accepted. What sort of strings will be accepted by this machine? Here again you see that if you take any string A, B, A, B, 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 something like that, it will be accepted. A, B, A, B, B, B will be accepted. But the condition is the length of the string should be divisible by 3. So, if you take just A alone, starting from here you will go here, it will not be accepted, or if you take 5 letters 1 A, B, B, you will reach this state, it will not be accepted. If you take a 4 letter one A, B, B, A, say starting from here A, B, B, A, you go to Q1, it will not be accepted. Any string of A's and B's will be accepted provided the length is divisible by 3. So, the language accepted or L of m or T of m is the set of strings x, x belongs to sigma star, of course, sigma is a b here, a comma b, and the length of the string is of the form 3k. K is an integer, k an integer. This is another example. Like that we can consider several examples. Now, let us see how an integer can be represented by this, and a Fortran identifier or a Pascal identifier will be accepted by this. Let us take the alphabet sigma to be, I shall use only capital letters A to Z and 0 to 9. I am just taking only capital letters, small letters also can be taken without in some other example, but here the alphabet consists of the symbols A to Z and the digits 0 to 9. Now, a Fortran identifier has a maximum length of 6, maximum length 6 Fortran identifier, and it begins with the letter A to Z, and afterwards you can have letter or a digit. So, that can be represented by a state diagram like this. You start with Q0, the initial state, then Q1, Q2, Q3, Q4, Q5, Q6. So, it begins with the letter A to Z. Starting from Q0, if you get a or a Z, A, B, C, D, any Z, you go to Q1, and it can be just that, you may end there also. So, this also happens to be a final state, but you can have 2 letter identifiers. So, the second symbol can be A to Z or 0 to 9, A to Z or 0 to 9. Then you go to Q2, again you can end up here or continue further. So, this also happens to be a final state. Then 3 letters, an identifier consisting of 3 symbols. The first one of course is the letter, second one is a digit, third one can be a digit or a letter. So, you go here. The fourth one is again, it could be a to Z or 0 to 9. Then this can again be a final state. We can have a fifth letter which is A to Z or 0 to 9. Again, this can be a final state, this also can be a final state. Sixth letter can be a letter from A to Z or 0 to 9. In Pascal, you do not have the limit on the length of the thing. So, suppose I use only capital letters, then you can have like this, any number of symbols you can have. The first letter has to be A to Z letter, then you may get Q1, A to Z or 0 to 9. Of course, I should also have something like the identifier cannot begin with a digit. So, if you get 0 to 9, I should go to a digit state and like this A to Z 0 to 9. So, a Pascal identifier can be given by this, a Fortran identifier can be given by this. An integer beginning with a 1 can be denoted, an integer should not begin with a 0. How do you represent an integer? Using a finite state diagram. initially you have q1. The first symbol you do not want to be any integer, decimal integer. So, 1 to 9 if you get, you go to q2, then it can be followed by any digits 0 to 9. So, this is this diagram represents an integer. Of course, when you get a 0, you do not expect it to begin with a 0, you go to a dead string and so on. So, you see that you can represent identifiers and integers using a state diagram. You can also represent something like 10.72.673 like this, a decimal number like this using a state diagram. Initially, you will have an integer q0, q1, then it can be followed by any digit, then a decimal point. So, here I am just writing those symbols will lead you to final states. Here the alphabet will also consist of a dot. So, when you do not get a proper thing, you have to go to a dead state. That portion of it I am not marking on the diagram. q3, and in q3 you may get any digit 0 to 9. Here 0 to 9. So, this represents a decimal number. In lexical analysis part of the compiler, you have one finite state automaton to represent the identifier, one to represent integer, and one to represent keywords and so on. So, all these finite state automaton will work together on the input. The input is the program is taken as a sequence of symbols. It will work on this, and whenever you recognize an identifier or an input or a special symbol, logical operators like that, you will take it as a token, and that will be entered in a proper table, a symbol table or a constant table, and you will put it there, and corresponding action will take place. Then the parsing will start taking place. So, that recognizing each one as a token is called the lexical analysis, and that is called a lexical analysis. And in this part, the finite state automaton plays a very useful part. Not only that, in text editing, suppose I want to replace a particular portion of a text by some other thing, that particular text alone can be represented by a finite state automaton, and in that you will remove that and replace it and so on. So, the same idea is useful in text editing also. So, this is one of the very important use of finite state automaton, and one of the things you must notice here is that when you are in a particular state and when you get a next symbol, the next state is uniquely determined. So, whatever we have considered today is called a deterministic finite state automaton. Whatever we have considered, that is called a deterministic finite state automaton. In contrast to this, you may also have non-deterministic finite state automaton, about which we shall study in the next lecture. In the deterministic finite state automaton, the mapping is from k into sigma into k, whereas in the non-deterministic finite state automaton, it will be from k into sigma into finite subsets of k. We shall consider some examples and see whether the power is really increased or not. The power will not be increased. Non-deterministic automata also have the same power. one more thing is the language accepted by a finite state automaton is called a regular set. It is called a regular set. Okay. So, in the next class we shall see more about finite state automata, in fact non-deterministic finite state automata, and also some minimization procedures.